All right, this is part 2 of the gases chapter, and this part will involve several different calculations involving gases, and you can stop at any point and scroll back and sit there and try and solve the problem yourself, and then you can watch how I solve it. So that's highly recommended with these with these gas problems, so you get used to all the little subtle points associated with getting the right answers. So this law is associated with all variables changing P, V, and T. So the gases that we looked at in the last chapter was PV, P1, V1 is equal to P2, V2 when temperature is constant. That's Boyle's law and so on. Let me just actually show you something interesting here with this relationship. If temperature is constant, that means it's the same. So at constant temperature, the denominators here cancel out, and you have P1, V1 is equal to P2, V2. If the volume is constant, then you have the law of Gay-Lussac. So V1 is equal to V2, so it cancels out. We say constant volume. P1 over T1 is equal to P2 over T2. And then if you have constant pressure, that's going to be the condition for Charles' law. If it's the same, then it cancels out, and then you have V1 over T1 is equal to V2 over T2. So if you remember this equation, you can come up with the other three, which is really nice. All right, so this is the case where all three variables are changing. We have a gas that's initially at a pressure of 200 torr, a volume of 300 mils, and a temperature of 26 degrees C. And here the volume's decreased and the pressure's increased all at the same time, and what will be the final temperature. So I strongly recommend that you write down all of your, that you make a list, you write all your variables down, all your information, and I would do it this way: P1, V1, T1, P2, V2, and T2. So with this equation, you want to have the units the same on both sides. You don't have to have liters. You could use milliliters because the milliliters are going to cancel. You can use atmospheres and atmospheres, torr and torr, millimeters and mercury, but you know they have to be the same, and those units will cancel. With temperature, there's no choice; it has to be in degrees Kelvin. All right, so then let's see. P1 is going to be equal to 200 torr. Let's go ahead and put that in atmospheres. You don't have to. You could pick your other pressure and put it in. Let's see, let me look at that now. Yeah, you have atmospheres for P2. So let's go ahead and take the torr, divide 760 torr in 1 atmosphere, and then the answer to that is going to be 0.26 atmosphere. All right, then your volume is 300 milliliters. Let's go ahead and put that in liters, 0.3 liters. And this is not a study of significant figures here. We don't know if there's a decimal point there or not. Let's just not worry about that. So T1 is 26 degrees C, and you're going to have to add 273 to it to get your Kelvin temperature, which is going to be 299 Kelvin. All right, then you have P2. P2 is going to be 0.60 atmospheres, V2, 0.25 liters, and what will be the final temperature? That's what we're looking for. Okay, so that's what I do. I got to write it all down and make sure all your units are the same. Then you say P1 V1 over T1 is equal to P2 V2 over T2. We're going to solve for T2 here. So T2 will be equal to P2 V2 T1 divided by P1 V1. Just play around with that a little bit until you see that's the situation. All right. So we have 0.60 atmospheres, which is going to be P2. V2 is 0.25 liters. T1 is 299 Kelvin divided by P1, which is 0.26 atmospheres, and V1, which is 0.3 liters. And if I got that right, this is going to work out to be 575 Kelvin. And then if you subtract the 273 from it, you have 302 Kelvin, not Kelvin, sorry, degrees C. So T2 is 302 degrees C, or 575 Kelvin. 575 Kelvin would have been just fine. But if you go back and look at the problem, you see that the temperature has gone from 26 degrees C to 302 degrees C, as the pressure has gone from 0.26 to 0.6. So the pressure's increased, the volume has decreased, and the temperature goes up. So it's hard to predict which way it's going to go when you get the three variables changing. All right, so on this slide, I want to derive the ideal gas law. And you know from Boyle's law that volume is inversely proportional, I should say, to 1 over P, or inversely proportional to P. Volume is proportional to T, that's Charles' law. Volume is proportional to N, which is Avogadro's law. So you can put that all together and you say the volume is proportional to N, T, and it's inversely proportional to P. So you can change your proportional constant of proportionality, to equal sign times a constant. So alpha, the proportional sign, becomes equal to a constant. And then you're going to call the constant R. Okay, so proportional is equal to a constant, which we're going to call R here. And then you can rearrange it and you get PV equals nRT. So this is the ideal gas law, but one of the most important ones of all the gas laws that you've seen so far. Now, for the gas law, notice you've got moles in it. So if you have any problems involving moles, or let's say you solve for moles and then you have to go to grams, you want to know how many grams are associated with a certain pressure and volume and temperature, you'll be using the ideal gas law. So whenever you have moles or masses, that's the way to go. Okay, so now what is the value of R? That's the constant. And you take PV equals nRT and solve for R. So you have PV is equal to nRT, solve for R, so it'll be PV divided by NT. Okay. Now, if you use STP conditions, remember that as standard temperature is 273.15 Kelvin, which is 0 degrees C. Standard pressure is 1 atmosphere. And do you remember the molar volume from the last section that we looked at, that under STP conditions, the volume of 1 mole of an ideal gas is 22.4 liters. So this would be the volume of 1 mole associated with standard temperature and pressure conditions. So you just plug all that into the ideal gas equation and solve for R, which is this very important number here, 0.08206 liter atmospheres. So you can see liter atmospheres per mole per Kelvin. And whenever you're dealing with gases with liters and atmospheres, you need to use this value of R. It's something you should memorize. Actually, all three of these are, probably the first two are good to memorize. When we study thermodynamics coming up in the next chapter, you will see that we are also talking about the same constant R, but it has a different numerical value because it's in joules instead of liter atmospheres. So there's an equivalent between the number of joules and the number of liter atmospheres. This is a unit of energy. You wouldn't think so, but it is. And, we'll study that anyway. So calories, that used to be the standard, and it used to be about 2 calories associated with 8 joules, or 1 4. So that ratio is 4.184. You don't need to know any of that, but it's just numbers that you see from time to time in your reading. Anyway, just focus on this one for the gas chapter. Okay, so then here is a problem that will involve the ideal gas law. So it's going to be PV is equal to nRT, and the question is how many grams, so you can always solve for moles and convert to grams, right? So how many grams of at a pressure of 300 millimeters of mercury in a volume of 500 mils at 25 degrees C. Okay, so you got pressure, volume, moles, and temperature. Now you're going to use R is equal to 0.08206 liter atmosphere per mole Kelvin. So the units for pressure, volume, and temperature have to match these units right here. So pressure has to be in atmospheres. You're given in the problem that it's 300 millimeters of mercury. You want to divide by 760 millimeters in 1 atmosphere to get let's put that right here, 300 divided by 760.395 atmosphere. Okay, the volume given is 500 milliliters. That's going to be 0.5 liters. You're going to solve for moles with this problem, then convert to mass. And the temperature is 25 plus 273 Kelvin, and that'll be equal to 298 Kelvin. That's room temperature. Okay, so then we're going to say N is equal to PV over RT. Make sure you don't have this flipped. Lots of times students will put N is equal to RT over PV, but think about solving for N and how to do it correctly. So N is equal to 0.395 atmospheres times 0.5 liters divided by 0.08206 liter atmosphere per mole per Kelvin, and then the temperature is 298 Kelvin. All right, so solve for N. N is going to be 0.00807 moles of N2. And then you want to get mass of nitrogen. So you're going to take your moles, multiply times grams per mole times the molar mass, 14 for nitrogen. So double that, 28 grams N2 per mole of N2. Mass equals 0.23 grams of N2. Okay, so that is a very, very powerful equation. You can come up with masses and moles and under different gas phase conditions. Two are contained. All right, the next law is Dalton's law of partial pressures. And for this one, just think about blowing up a balloon. So you blow up a balloon, and what's inside the balloon? Okay, it's going to be your breath, right? So your breath has got carbon dioxide in it, a little bit of nitrogen, maybe a tiny bit of oxygen in there as well. And so you got at least 3 gases. There's some water vapor there as well, right, from your breath. So you got 3 or 4 gases present, and you can talk about the contribution that to the pressure that each one makes. So you might have, half an atmosphere of oxygen or carbon dioxide rather, things like that. So you want to know what the total pressure is in the balloon, and it's going to be the sum of the partial pressures, the pressures of the individual gases. You just add them up. As long as the gases are behaving ideally, you can just add them up. There's no problem at all, and you get the total pressure. That's Dalton's law. Okay, so this is a problem that's a little bit weird, but a kind of a typical one in the laboratory. And this one, you have, I'm going to draw a picture here to help you decipher this. Draw a picture of a manifold. In the olden days, they were made out of glass. Nowadays, a lot of them are made out of metal, but it's a tube with some ports on it with stopcocks. Let's put 4 of them there. And the tube comes around like this, and maybe there's another one up here. A couple of them up there. as well, and then it comes around like this. So you can, this is glass, let's say, you can open this stopcock here, hook it up to a vacuum line, and you can pump the air out. So you got almost no air in there at all. All right, then you close it back up. So you have a vacuum system. Then you can put on these containers, gas containers. Actually, this third one, we're going to put a freeze out tip on it. So it's like this, and then it's got a tip on the bottom of it like that. So, all right, bear with my drawing here. So the idea here is that the, well, first of all, you're going to keep these stop clock, the red stop clocks are going to be closed. You're going to open these up here, and basically you're going to open this and you're going to suck all the air out. You're going to pull a vacuum on this entire system up to these stop clocks right here, and then close it back up. So now you have a vacuum on the system. All right, so the first one contains nitrogen, and this is 200 milliliters. We have 25 degrees C and 250 torr. So those are the conditions for the first one. The second one is oxygen. The second one has 350 milliliters. The temperature is the same. So in fact, the temperature is the same all the way through. We're just going to get rid of that temperature. And then you have 300 torr here. Let's just get rid of that temperature right there. It's easier if we do that. All right, now the goal is to take the nitrogen and the oxygen and put it into the empty flask. And actually, when we were pulling a vacuum, you open this up here, and you actually pull a vacuum right there, and then close it back up. So what we want to do is bring the nitrogen and oxygen over into this empty flask. And the technique for this is to use a dewar. It's like a thermos bottle, and you fill it with liquid nitrogen, and you put the tip, this freeze out tip on the glass bulb, into this thermos bottle or this dewar of liquid nitrogen. And then we're going to open these up, this one and this one, while this is all closed here. So what happens, think about it, think about the nitrogen first. If it's in gas phase, it's going to expand it into the whole system, including in here. When the nitrogen experiences the liquid nitrogen, which is at 77 Kelvin, so this is really cold, 77 Kelvin, then it'll freeze. So you're going to get some nitrogen that'll freeze in the tip. And as you freeze in the tip, you lose the gas that was here, so more gas will move in until all of the gas has been transferred into and frozen into the tip of this tube, this bulb. Okay, so then you open this up. Same with the oxygen. You can take the whole thing and freeze it in liquid nitrogen. So then the next step is to close this stopcock. Whoops, close the stopcock right there. And then take off the dewar, let it warm up, and then all the gases are going to reappear as they're melting out of the solid phase. So in the end, you've got a mixture of N2 and O2. So you've got the condition that the new volume here is 300 mils. So this volume is 300 milliliters. And the question is, what is the pressure of the two gases in the new volume? All right. Okay, so that is a complicated thing, but we bring it up because it's just one of those things. If you're, a chem major, sometimes even in biology, you might run into this type of experiment where you want to move some gases around and mix them together. Okay, so now let's go ahead. We're going to use Dalton's law of partial pressures here. Think about it for a moment. You've got a new volume, which is 300 mils, and your gases are contained in those. You have a new partial pressure of nitrogen and a new partial pressure of oxygen. So you can calculate them and add them up to get the total pressure inside of here when it's back up at room temperature, 25 degrees C. So then you're going to say P1V1, that gas came over here. P2 is what we're going to solve for, times V2. Then you do the same thing for the oxygen. So P1V1, those are the moles that you're carrying over here. And then that's equal to P2V2. This is the same V2, right? They're both in the same volume. So you solve for P2 for the O2 and then add them up. So that's what we're going to do here. Okay. So for the oxygen, you have 300 torr times 350 milliliters is equal to the pressure in the new flask of the O2 times 300 mils, which is the volume of the new tube flask. PO2 is going to be 350 torr, which is equal to 0.46 atmospheres. We don't really need that, but sometimes people convert. So that's fine. Okay, and then for the N2, similarly, we'll say 250 torr, P1 times V1, 200 mils is equal to P2 for the N2 nitrogen, so final partial pressure of the nitrogen times the volume of 300 mils, which is the volume of the final flask. All right, solve for a partial pressure of N2, and that'll be equal to 167 torr, which is equal to 0.22 atmosphere. All right, so then we can add them together. We're going to use Dalton's law of partial pressures here. P total is equal to 350 torr plus 167 torr, and that is equal to 517 torr, which is 0.68 atmospheres. Okay, now that you're not going to use this too often, but it's kind of one of these, interesting problems. You can use the principles of some of these simple gas laws and come up with a total pressure for a mixture. So anyway, okay. Then let's see. The next topic is mole fraction. And for mole fraction, it's a concentration. So we could talk about mass percent, mole percent. You could talk about the mass fraction or the mole fraction. They're pretty similar in terms of the definition. So we'll start then with this definition for mole fraction. This is something that you can use for solutions as well. You can say the mole fraction of one of the components. Let's say you have this is the gases chapter, but you could have solution with components A and B. But if they're gases, you can imagine that. So you got two components, A and B. So the mole fraction of A will be the number of moles of A divided by the total moles, which is Na plus Nb. So Na over N total. Mole fraction of the other one, will be Nb divided by N total. And so what happens when you add them together? Na plus Nb divided by N total is going to be equal to 1. All right. Now, another equation that's useful here is taking, let's see here. So if you want to solve for Na, you can take N total, multiply that times both sides. You get Na is equal to mole fraction times N total. Similarly for B, Nb will be equal to mole fraction times N total. And these, there's a group activity on this issue here. Combines a couple of different equations to use to solve a problem, and this is one of them right there. All right, now this is for moles, but you can say that moles are proportional to pressure. And you can just do a substitution here. Pressure of A, that's a partial pressure of A, divided by the sum of the partial pressures, which is equal to the total pressure. And you can do that because PV equals nRT. So P is proportional to N, and all the other constants just cancel out. Constants and variables cancel out. So similarly for B, remember we said moles of B divided by total moles. Now it's partial pressure of B divided by the sum of the partial pressures, which is P total. The sum of the two mole fractions is 1. And similarly, partial pressure of A is equal to mole fraction times P total. And similarly for B. All right, so this one is exclusively for gases. The last one in terms of mole you can use for solutions are for gases. Okay, so here is a simple problem. The mole fraction of N2 in air is 0.7808. Okay, so like 78 mole percent, right? Calculate the partial pressure of N2 in air when the atmospheric pressure is 760 torr. So this is a simple problem. We have mole fraction of A is equal to partial pressure of A divided by P total. Solve for partial pressure of A, and this will be equal to mole fraction times total pressure. The mole fraction in this case is 7808, and then the total pressure is the atmospheric pressure, which is 760 torr. So this works out to be 593 torr of N2. And that's it. That's a simple problem. So think about it with air. If you're breathing in 760 torr, or 1 atmosphere pressure, 593 torr of that is nitrogen, according to this calculation. All right, now for the hard one. I think that this is probably one of the hardest problems to do for the entire course, because it combines stoichiometry with the gas laws. And you have to, for this problem, you got your moles, 4, 5, 4, and 6 for this chemical reaction. And the coefficients here are going to be proportional to the moles. That's what I meant to say. And so you could do PV equals nRT to get moles, PV equals nRT to get moles, and so on. And then you look at the coefficient ratio for the mole ratio. So to calculate amounts of product formed and amount of one of these that's left over, because one of them is, the other one's going to be the limiting reactant. All right, that's a lot, and we will just dive right into it. Okay, so I'm just going to write down below. I'm going to write out the equation here so I can write underneath it. So 4NH3, it's all gas phase, 5O2, 4NO, 6H2O. Okay, and let's see. So for oxygen, you have 2.15 atmospheres at 35 degrees C. For ammonia, you have 4.32 atmospheres at 40 degrees C, and the volume is 1 liter. So you've already mixed the gases together. It's not like the last problem where you have to figure out the new volume and moles and pressures and things. It's already mixed together. They're both together in a 1 liter flask. So the question is, what will be the pressure of NO and water? Those are the products. And then what will be the final pressure? So that's going to include the unreacted reactant that is not the limiting reactant. All right, so let's go ahead and just make some notes here. And for ammonia, you have 4.32 atmospheres, 40 degrees C, 1 liter. For oxygen, 2.15 atmospheres, 35 degrees C, and also in 1 liter. That's all you have. So you have quantities of more than one reactant. You have to figure out which one is going to determine how much product will be formed. So you're looking for the limiting reactant. So in order to do that, you got to convert to moles first. So we're going to convert to moles here. For the ammonia, N is going to be, N will be equal to PV divided by RT. And we're going to use atmospheres, 4.32 atmospheres. Then we're going to take the temperature as 273 plus 40, which is 313 Kelvin. What happened? Oh, so this is 1 liter. R is 0.08206 liter atmosphere per mole Kelvin. And the temperature is 313 Kelvin. So N for ammonia is going to be equal to, double check my numbers here, 0.168 moles of NH3. Okay, then we're going to go to moles of oxygen. So oxygen, N is PV over RT, and you have here pressure is 2.15 atmospheres times volume, which is 1 liter, divided by 0.08206 liter atmosphere per mole Kelvin. And you really should put your units in there. They help keep you straight. And the pressure here is 308 Kelvin. You have to have it in Kelvin. So, and in this case is 0.0851 moles of O2. Okay, now let's not even confuse things here. Now we're going to look for the limiting reactant. So we're going to calculate the amount of NO from each one of these. And we're going to take 0.168 moles NH3. And we're going to use the mole ratio, ammonia to NO, nitric oxide, it's 4:4. So we're going to say 4 moles of NO for every 4 moles of NH3. And the amount of NO formed will be 0.168 moles of NO. Then we're going to take our other reactant, oxygen, 0.0851 moles of O2. And the ratio of the NO and the oxygen, so let's look at that. It's 4 NO for 5 O2s. So we're going to say 4 moles of NO for 5 moles of O2. So 4/5 of 0.0851 equals 0.06808 moles of NO. So we are going to pick the smaller of the two, and then that will make the O2 the limiting reactant. Okay, 0.06808 moles of O2. All right, so we know what the limiting reactant is, and now we're going to use the limiting reactant to calculate everything else. If you look at your reaction again, now we're going to go after the water using the limiting reactant, which is O2. So it's going to be a 6:5 ratio for water to O2. Okay, and so it'll be, we're going to calculate the moles of water using the limiting reactant. So 0.06808 moles of NO, and then this is going to be a 6 moles of water for every 5 moles of O2, and this will be equal to 0.102 moles of water formed based on the limiting reactant. Okay. All right, the next part is to figure out the leftover ammonia. So if O2, limiting reaction is O2, if the O2 is completely consumed, then there's going to be some leftover ammonia as well. So that's that two-step process. The amount of ammonia, and we're going to use the limiting reactant O2 again. So first we want the amount used up. So we're going to say 0.06808 moles of NO, and it is a 4 to 5 ratio, 4 moles of NH3 for every 5 moles of O2. This is going to be 0.0681 moles of NH3 consumed. We know how much we started with, right? We got that way at the top there, 0.168 moles of ammonia right here. So that minus what was just used up will be the amount that's left over. So the amount left over is going to be 0.168 moles NH3 initial minus 0.0681, let's just call it 0 here, keep it simple, moles NH3 used up. Subtract those two, and you're going to get 0.168, this is 0.0680 moles of ammonia, and that difference will be 0.1. So 0.1 moles of NH3 left over. And all three of those are going to contribute to the overall pressure of the system. All right, 2 ways to get to the end of the problem. And we've got, let's put some green on this here. So we got moles of NO, moles of water, and moles of ammonia. That's what's left. If we had those in partial pressures, we could add them up to get the total pressure. So we could do that. Let's go ahead and get pressures. So we want the pressure, partial pressure of NO. We want the partial pressure of water, and then the partial pressure of ammonia. And it's nRT over V. Okay, so moles are going to be 0.06808 moles NO. R is 0.08206. Let's just leave up the units here. Liter atmospheres per mole Kelvin. This problem is at 298 Kelvin, and you're dividing by 1 liter. So the partial pressure of NO is equal to 1.67 atmospheres. Okay, similarly for water, you have 0.102 moles of water times 0.08206 times 298 Kelvin divided by 1, and that is equal to 0.249 for water, 2.49 atmospheres. Come on in. So we have 0.1 moles of NH3 left over times 0.08206 liter atmosphere per mole Kelvin times 298 Kelvin divided by 1 liter, and that one is going to be 2.44 atmospheres. So according to Dalton's law of partial pressures, P total then will be equal to the sum of those three, 1.67, 2.49, and 2.44 atmospheres. That equals 6.60 atmospheres. Now, that's the final answer. It's pretty long. There is another way to do this problem. I'm not going to give you the details here, but it's simple. Just depends on whether if the question asks for the individual pressures to be added together to get the total, or if it just wants the total, because the other way to do it would be to say P total would be equal to, it's going to be nRT over V, so it would be the number of moles of nitric oxide plus the number of moles of water plus the number of moles of leftover ammonia times RT divided by V, right? You get the same answer instead of having to convert to each individual partial pressure. So, all right, that is the longest and hardest problem for the entire course. Okay, next slide. So here we are looking at some easier stoichiometry problems. This one involves molar volume. Excuse me. Molar volume, if you remember, is 22.4 liters. That's the volume of 1 mole at STP conditions. So how many grams? You can already, if it's asking for grams, you know you're going to use PV equals nRT. Will form when 1.24 liters of hydrogen gas at STP conditions reacts with 3 liters of O2. So before we get to the PV equals nRT part, let's do the stoichiometry part. And I'm going to write the reaction over again here. So 2 hydrogen plus oxygen forms 2 waters. And the hydrogen is 1.24 liters. The oxygen is 3 liters. And the question is how much water? So that's what we're going after there. This is a limiting reactant problem. You have quantities of both reactants and you're trying to figure out one of the products in this case. So instead of using PV equals nRT and converting each one of these numbers to moles, so you could say, you know, you've got standard temperature, 273 Kelvin, standard pressure, 1 atmosphere. This is the volume. You could calculate the moles and then just do the mole comparison. You can use a little trick here. And the trick is that Avogadro's law says that volume is proportional to moles. So you can just take volume ratios instead of mole ratios. So the first thing we're going to do is test for the limiting reactant. It's the same procedure, but we use volumes instead of moles. So you take 1.24 liters of hydrogen and you look at the coefficients in the balanced equation and say there's 2 liters of water vapor formed for every 2 liters of hydrogen. So this is going to be 1.24 liters of water formed. Then you take your other reactant, 3 liters of O2, 2 liters of water is formed for every 1 liter of O2 consumed. So this is going to be 6 liters of water. And of course our procedure is to pick the smaller value as the correct value. And then that means that the hydrogen is the limiting reactant. So it doesn't matter so much what's the limiting reactant at this point. We're not going to use it going forward, but this certainly is the correct amount of water that's formed. So the next step is to just use, you could, at this point with liters, you could use PV equals nRT to get N, and then go to grams. Or you could use the molar volume, since this is an STP condition situation. So use the molar volume in this point. So you say 1.24 liters of water. And you can say for every 1 mole of gas phase water, that corresponds to 22.4 liters of gas phase water. And you get 0.055 moles of H2O. So we didn't use PV equals nRT, we used a molar volume ratio instead. All right, so the last step is to take the 0.055 moles of water and multiply times molar mass, 18.02 grams per mole. And then you get 0.997 grams of water. So that is a very different kind of problem and a little bit easier to work with, right, than the last one. All right, the next topic is gas density and molar mass. What's the relationship between those two? So you can use PV equals nRT. And you can use the relationship that the number of moles is equal to the mass divided by the molar mass, right? You have grams divided by grams per mole will give moles. So you can plug in here and say that PV is equal to mass over molar mass times RT. All right, then you can, I guess in this equation it's just capital M, but you can use capital M, lower m, or you can say mm per molar mass, doesn't matter. All right, then you want to solve for pressure here. So pressure is equal to mass. Make the mass divide the volume, divide the mass by the volume, and then you have RT over molar mass, and of course mass over volume is density, right? So then you've got pressure is equal to density RT over molar mass. That's how you get that equation, and this is just a good one to know. I mean, you guys it's an online course, so of course you got all your equations in front of you when you're being tested, but it's a real good idea to think about just memorizing some of these equations for later. All right, so then we're going to use this equation. Density of the gaseous compound is 1.34 grams per liter. Notice that densities of liquids are grams per milliliter, but because gases have such low density, it makes more sense to do it how many grams there are in a liter, 1.34 in this case. You got 298 Kelvin here and 1 atmosphere. Sorry, I keep getting interrupted. Okay, anyway, we are solving for the, what are we doing here? What's the molar mass of the compound? So we have molar mass is equal to dRT over P. Simple equation, simple plug-in problem. So this is going to be 1.34 grams per liter times 0.08206 liter atmosphere per mole Kelvin times the temperature, which is 298 Kelvin. And then you're going to divide by the pressure, which is 1 atmosphere. You can do the conversions and see that. So the molar mass then is equal to 32.8 grams per mole. And this is something that you could probably guess. This is an unknown compound, but something with 32 grams per mole in its gas phase. A good guess would be oxygen, right? So 16 times 2 is 32 for that. Probably is. All right then. Next slide, it's kinetic molecular theory, and these are the postulates of it. 4 postulates. They are that the molecules are very, very small, and there's large space between them in the gas phase. And the molecules are in constant random motion, so they're colliding with each other. Collisions for this particular model are considered to be elastic. And elastic means that when the molecules collide with each other, there's transfer of energy and momentum. But when the molecules collide with the walls of the container, no kinetic energy is lost. Right here. So, in other words, the energy within the system stays constant. And then also there's this interesting idea that the average kinetic energy of the system, so think about what that means. That's all the different types of energies of the molecules, rotations and vibrations and so on, plus all that translational energy where they're moving around in the system. And it's the average kinetic energy of the system. So that means you take all the different kinetic energies of the molecules, add them up and divide by the number of molecules to get the average, right? That's proportional to the absolute temperature. So I made it sound more complicated. Just keep it simple, that the average kinetic energy of the system is proportional to the temperature. Absolute means in degrees Kelvin. So here are two slides that illustrate some of these ideas. And this symbol here, that is the Greek letter mu. It's got a long arm on the left-hand side there. Mu, and that is the symbol for the molecular speed. And this is just an equation from kinetic molecular theory that it's equal to the square root of 3 times r times the absolute temperature, and then divided by the molar mass, so mm molar mass. And the important part of this is that you see that the speed of the molecules is inversely proportional to the square root of the molar mass. So as if you have a light molecule, so you have a small mass, then the speed's going to be high or the speed's going to be fast. So there's this inverse relationship here. If you have a heavy molecule, then the speed is going to be less or it'll be traveling slower. And we won't do any calculations involving 3RT over m square root, just sort of that basic idea. And the graph here shows that it's kind of the way they plot it's a little bit strange, but it's consistent amongst the different books. The relative number of molecules. So you can just think of, this might read instead the molecules that have a certain velocity. Or you could think of it in terms of percent. So you could say, that versus the speed. So, this point might correspond to, if it were in percent, 2% of the molecules are traveling at 100 meters per second. Then, 5% of the molecules are traveling with, 200 meters per second, like that. So then when you get to the top here, this is considered to be the most probable speed. The average speed that's referred to in these equations is actually, when you add up all the speeds and then divide by the number, there's a way to do that. The number isn't exactly on the max here. It's a little bit over here to the right. So doesn't matter. It's not important for what this is. All right, so then these would be two different molecules, A and B. And the one that's moving faster would be this one because the average here is around 1,100, 1,200 meters per second. And over here it's about 500. Excuse me. So the one moving faster, notice that you've got a broader distribution here, meaning, so with B molecules, which are lighter, more of them are moving at higher speeds, no doubt about that. And then the heavier molecule, the maximum speed you can get is around 1,300 in this example. So you see those principles just in terms of this graph. All right, the next one is the distribution of molecular speeds with regard to temperature. So it's the same equation, and now we're just looking at the fact that the speed is going to be proportional. Here, molar mass inversely proportional, but it's directly proportional to the temperature. Of course, it's the square root, but we don't care about that. All right, so same idea here. You have two temperatures for the same system, okay? And when it's, the T2 is going to be higher than T1, so you say T2 is greater than T1. And then you would say when the temperature is higher, more molecules are moving faster, right? The temperature is lower, they're moving slower. So you can see that, the average temperature here and here is directly proportional to well, we know it's the square root of the temperature, but we'll just say directly proportional to the temperature. And that's, the fourth principle of the kinetic molecular theory. All right, so then you can actually use that equation, and instead of speed, you can talk about the rate with regards to molecules that are traveling around in a container, for example. And we use the term diffusion and effusion, and we think about those, we can come up with Graham's law. So diffusion would be like if I take some perfume and I put it on my skin. It takes a few seconds before I can smell it, right? So the molecules move from the surface, and when they do, they spread out. That's the property of the gas. And then effusion is different. You have a container, I'll make it square here, all right, with a little hole in it, and you've got some gas inside. If there's a hole in it, the molecules can effuse out of it. So now the idea is if you've got two different types of molecules, right, one lighter than the other, so make the red molecules lighter, those molecules are going to come out faster than the blue ones. So this equation is telling us that the rate of, we can make the molar mass 1 being smaller than molar mass 2. So the lighter molecules will come with a rate that's higher than the heavier molecules. That's the idea here. And you can derive it from that last equation, but let's not bother with that. All right, so this is the equation that we're going to use. Graham's law applies to both diffusion and effusion. Excuse me. And you can already see that the units here are going to be different. Let me outline the units here. So we have hydrogen diffuses through a porous barrier at a rate of 52 milliliters per minute. Temperature's the same all the way through, so that's not the issue. And so it's milliliters per minute would be the rate. Okay, and then we want to know what the rate is for the oxygen. So you have hydrogen, which is light, oxygen, which is heavy, and you could set it up so that you could say, you could do it either way. We'll start with the oxygen being heavier in this case. On the top there, rate of oxygen divided by the rate of hydrogen. And we know the molar masses, so it's inverse proportionality. Hydrogen's a mass of 1, hydrogen's going to be a mass of 2. H2 will be a mass of 2. So we'll just, 2 sig figs, we'll say 2 grams per mole. And then for the oxygen, that's going to be 32 for the diatomic molecule. Okay, and that is square root of 1 over 16, which is 1 over 4, right? So the rate of O2 divided by the rate of H2 is equal to 1 over 4. And we are solving here for the rate of oxygen. So the rate of O2 is equal to 1/4 the rate of hydrogen. You just multiply the rate of hydrogen times both sides there. That makes sense because hydrogen's moving fast. Oxygen will move at 1/4 the rate of hydrogen because it's heavier, right? And so now you can just plug it in. You've got the rate of O2 equals 1/4 the rate of hydrogen, which is 52 milliliters per minute. And so the rate of O2 is equal to 13 milliliters per minute. All right, that's how you do that problem. Students tend to not think that question's going to be on a test, but I tend to put that on, so watch for that one. All right, almost the end here. There's a difference between the ideal gas model and the real gas model. So I mentioned this before with ideal gases that you can use PV equals nRT, which is an equation for an ideal gas, and you'll get the correct answers for whatever variable you're solving for, as long as you have low pressure and high enough temperature. And the idea is under those conditions, the molecules are not interacting very much with each other. They're not attracted to each other, because if they're attracted to each other, then their paths are going to deviate from straight line paths. Ideal gas molecules make straight line paths. Real gases do not. And so it changes the pressure and so on. And as long as the pressure is low and the temperature is high, then you can use all those gas laws that we've developed for this chapter. Real gases, on the other hand, they're associated with high pressures and low temperatures where molecules are interacting with each other more frequently. And this business about having volume, that goes back to Charles' law. This is the graph of volume versus temperature for gases. If you remember, the volume decreases as the temperature decreases. If it's an ideal gas, it's going to just keep going down until you get 0 Kelvin, which is minus 273.15 degrees C. So, if it's an ideal gas, it actually, in theory, is just going to continue to decrease its volume until it hits this point right here, this temperature point, which means that, in theory, molecules at this low temperature don't have any volume. So that's what this point is here. And, of course, real gas molecules do have volume, so you get condensation instead, as we discussed before. And then intermolecular forces, that's going to be the forces of attraction or repulsion between molecules. They don't exist in the ideal gas model, and so molecules just speed past each other without any interaction. Therefore, the pressure is going to be the ideal pressure. But if they do have forces, then they will interact. And if this is your gas phase container, here's a couple molecules. Here's this one, and it's, you know, in theory it would be straight line, but when it gets here, it's going to be interacting with that one. Maybe it pulls it this way, maybe it goes that way, it goes around like this. And we talk about pressure not only as force per unit area, but we talk about the number of times that the molecules strike the wall per unit volume. And so it's just a different definition, which basically boils down to the same thing. So the number of molecules that strike the wall per unit time for the real gas is going to be less. So pressures are going to be less for the real gas system. Anyway, that is the idea. And then the last slide here is called the van der Waals equation. And this is an equation that van der Waals developed to account for the non-ideality of gases. And you've got these terms here, the A term and the B term. A and B are constants. And basically you have to fit, each molecule according to the constants associated with them. We're going to skip this. But good to know about if you're an engineering student, that this is the first of the real gas models that was developed. There's some other ones that are better today, but this equation actually works pretty well. So if you had the constants and some volume and temperature, for example, the pressure that you solved for should be pretty good if you're going to use these numbers. All right, that's the end of the chapter.